Hi, I'm Umnik. I will be doing at Code regular contest 205, and I will try to explain what I'm doing on the way. I'm 3 minutes late as always, but that shouldn't matter. Problem A, 2x2 erasing. There is a grid with n rows and n columns, so it's square. Let RCD know the cell these coordinates. Each cell is colored black or white. It's black if it's what is that symbol? Octothorpe hashtag. And white if it's a dot. No, Octothorpe is a star symbol, right? What's the correct name? I don't know. You're given Q questions about this grid, so answer each of them. And this question, integers up, down, left, right are given, so find the answer to the following question. After coloring all cells that do not lie in this rectangle black, find the maximum number of times you can perform the following operation. Choose a pair of integers. So choose a cell that choose a 2x2 square that is white and color one of these 4 cells black. Okay, but since we're coloring outside into black, it just means that basically cut this rectangle and solve the problem on this rectangle. Okay, so it's actually queries to subrectangle. Interesting. When I see such a thing on grid, I think about like earlier formula for planar graphs, but that's not the same thing, because we can't have a cycle with a black cell inside. Okay, let's look at the sample. So on first query we will be talking about this 3x3 square. Yeah. And then can perform the operation twice. Is it just the number of 2x2 white squares? Because obviously after one operation I will break the squares that I have chosen. Like I choose a white square and paint one cell black. But on the other hand, I think I can just sort all the 2x2 white squares in like row major order, and each time just choose the upper left cell. Right? And like that will only break the square I have chosen. So the answer is just the number of 2x2 squares, and that should be easy to do, right? It's basically just 2D prefix sums. I have 2x2 squares that are good and that are bad, and I need to count the number of good 2x2 squares that are inside my subrectangle. So that's just two-dimensional prefix sums. Yeah, okay, that sounds right. It's just one test. Okay. My fingers are not listening to me. So I'm iterating over all 2x2 squares. The number of 2x2 squares is like n minus 1 by n minus 1. But then for prefix sums, I will increase both dimensions by 1. So it will be like n by n. And the prefix sum in point xy is like the sum on the rectangle with corner here is sum on rectangle without the last row plus sum on the rectangle without the last column, but without first row, last row and last column we calculated twice, so we subtracted back. But we also didn't count the cell that is downmost rightmost. So if it is good, I need to add 1 here. So if this is white and this is white, and those two are also white, then I need to increase it by 1. Okay, now I have my prefix sums. Up, down, left, right, and okay. I think I need to subtract 1 from all of them now. Like I used 0 indexation, but also like I'm counting 2x2 squares, not just points. So I think I need to decrement each one of them, and then the answer is the sum on the subrectangle, which is this. Well, certainly I should be able to understand if 0 is 0. typo. And that is good. For 4206113, that's correct. Problem B, triangle toggle. There is a complete graph with n vertices. Each edge is colored black or white. We are given m black edges, all the others are white. You can perform the following operation 0 or more times. Choose a triple of integers a, b, c such that they are different, and flip the color of the triangle on those three vertices. Find the maximum number of edges that can be colored black when you perform operations appropriately. So we want to minimize the number of white edges. Since in every operation we flip two edges that are connected to one vertex, we do not change the parity of the number of black edges connected to one vertex. Is it just the criteria and we can achieve everything with correct parities? Like, probably. A was accepted. So I can make every edge except for the all edges that are adjacent to vertex 1. I can make them black just by take that edge if it's white and like take endpoints of that edge and vertex 1 and flip that triangle. Like I will fix all the edges except the ones that are connected to vertex 1 because like I used it to fix everything. So now I have some number of white edges from vertex 1, but that is not the minimum because so for all the vertices except vertex 1 I achieved their maximum because like each one of them has either 0 or 1 white edge, and like I know that the parity is fixed, so if it has 1 white edge, like it must have at least 1 white edge. But for vertex 1 maybe it's not optimal, but I can take pairs of white edges that go from vertex 1 and flip the corresponding triangle. That will decrease the number of white edges, but also like for all vertices except vertex 1, it will still be true that their white degree is 0 or 1. And so I will do that while I have at least two white edges from vertex 1. After that, my white edges are a matching because like every vertex has white degree 0 or 1, and that is just optimal. Because if vertex has white degree 1, it means that it was odd at the start and it will always be odd. So the answer is the maximum number of black edges I can achieve. I should only print the number, right? Okay. So the maximum number of black edges I can achieve is and choose 2, that's the all edges, minus the minimum number of white edges. And the minimum number of white edges is number of vertices with odd white degree divided by 2, because like I count each edge twice in that. So I just read the input, calculate the parity of white degree for every vertex, and then take like n times n minus 1 divided by 2 minus the number of white degrees also divided by 2. Number of odd white degrees. Okay. But I could have actually constructed the answer in time proportional to like n square, which is the size of the answer, but n square is big. But like yeah, if they wanted me to print the actual flips I want to do, I would be able to do that. So initially the parity of degree of white degree is parity of n minus 1. And then for my m edges, I flip both parities. Problem C, no collision moves. There are n people on number line. Person I is initially at coordinate Si and wants to eventually move to coordinate Ti. It is guaranteed that all the starting and ending positions are distinct. You fix one permutation and perform n operations in order. In this operation, you move person Pi from coordinate SPI to coordinate TPI along the shortest path on the number line. However, if there is another person on the movement path, a fight occurs. Determine if there exists a P such that no fight occurs, and if it exists, find one. So we need to choose the order in which we move the people on the given segments, such that no two are ever at the same position. That means that the initial order and the final order must be like the same relative order, because we cannot swap relative position of two people, because like one will move through the other anyways. So like it should be some kind of like just people are in some relative order in some positions, and we like shift them, like each one of them can move somewhere, but the relative order must stay the same. If that's not true, it's certainly impossible. If it is true, it should be possible, right? There always should be a move that doesn't break anything. Yeah, like I can imagine it as a like kind of correct bracket sequence, um, or I don't know. Well, no matter. Just look at all the points we have, like starting points, we have ending points. Let's put uh, +1 in all the starting points and -1 in all the ending points. If my first, like leftmost point is a -1, so it's an ending point, then it surely is an ending point for the leftmost person. So let's just move them there right now. It's always good. Basically, we take them and move them out of the way. Nobody wants to go there other than him, so just take them and move them to the final position. Otherwise, my first point is a starting position. But then I can like move, I can scan the line like, left to right, and there will be a point. I will maintain the balance, like the sum of numbers I encounter. There will be a point where the balance is zero because I know that in the end balance is zero, since I have the same number of pluses and minuses, right? So there will be the first point where balance is zero. I state that, like, because we started with a plus, this point will be a minus, and I can just move the corresponding plus to that minus. Um, because basically everyone who is on the left of that point wants to stay on the left of that point, and everyone that is currently on the right, and then they also want to be on the right. So if I take that person and move it here right now, I basically split my problem into two independent problems, and nobody will want to move through that point anymore. So I can always do that. Okay, that's so if I just do it one by one, that will be n squared. But I think I don't have to do it one by one. I can just uh, like do a scan line and maintain some kind of, I don't know. I want to say that I can just maintain a balance, but that's not exactly right. Like when I when I match someone to that minus, like I move them there, but then maybe previous minus also became good. I mean, it must have become good actually. Since all the balances are correct. So is it true that just for all of those people, I just take them from right to left and send each one. Yeah, all of them want to move to the right. Is it true then that I can take all of the people that want to move to the right and process them right to left, and take all the people that want to move to the left and process them from left to right? And all of those things are independent? I guess so. Like, if they're not intersecting. I think that must be true. Like, if I draw it on two parallel lines, like I have a line with all the starts and line with all the ends, if I connect, like, start with the corresponding end, those segments must be non-intersecting, because if they are intersecting, then there is an inversion, and the answer is just impossible. Otherwise, like, two segments that move in the opposite direction, they cannot intersect at all. So the only thing I need to be careful about is, like, separately processing people that want to go to the left and people that want to go to the right. And for those, like, it should be clear that the ones that go to the left, I want to process left to right, because, like, I'm moving each one out of reach of everyone else. And the ones that want to move to the right, I want to process from right to left. Okay, that was unexpected for me, but I mean, I proved it, so it must be right. I need to print the indices, right? Okay. So I will sort all the people by their starting position, then I need to check that the ordering by the right position is the same one. So I sorted by the left by starting positions. Now finished positions also must be sorted, so I'm just checking that. Okay, then it's possible, and people that want to go to the left and processing left to right. I mean, they're all just and people that want to go right, I need to process from right to left. B was accepted. Problem D, non-ancestor matching. You're given a rooted tree with n vertices numbered from 1 to n. Index 1 is the root, the parent has strictly smaller index. That's good. Initially, all vertices are colored white. You can perform the following sequence of operations 0 or more times. Choose a pair of integers UV that satisfies all the following conditions. U is smaller than V, both vertices are colored white, and U is not an ancestor of V. Color vertices U and Y black. Choose a pair. For some reason I read it as all pairs, but no. I'm choosing one pair. That one is, well, their LCA is not one of those vertices. Well, it says that U is not an ancestor of U, but V cannot be an ancestor of U because V is bigger by index and all the ancestors are smaller. Here U is not an ancestor of U means that you cannot reach vertex U from vertex V no matter how many times you perform the operation of moving to the parent. Find the maximum number of operations you can perform when you perform operations in an appropriate order. Surely the order doesn't matter. Well, yeah, the non-ancestor matching, like they, I guess they formulated for the people who don't know what matching is, but it is exactly that. Like we need to find the largest possible set of pairs of vertices that are pairs are not non-intersecting, because like in every operation we color we take two white vertices and then color them black, so we mark them as used basically. And those vertices in one pair must not be like ancestor of one another. Okay, so like if we build a graph like connecting two vertices when they're not like not on one vertical path, we just want to find maximum matching in that graph. Okay, it says also accepted. But n is very big. We cannot even build that graph, not to say run any matching algorithm on it. But we can do some greedy, right? So we have a tree. In the tree there is a root, but root cannot be used in any pair, right? Because it's an ancestor of everything. So we cannot take it at all. But we can look at the subtrees of the sons of the root, and if we take two vertices from different subtrees, we can match them. Can we just match all of it, like by matching one subtree with the other? Sometimes yes. If we look at the sizes of those things, so the sum of the sizes is, well, if it's the root, then it's n minus 1, but like I will remove that because like later we will need to do kind of similar thing but lower, so I don't want to just say that we're using the root here. So let's say that the sum of sizes is some number a. Obviously, if a is odd, we cannot match everything, but maybe we can match like almost everything. Can we get a divided by 2 rounded down? Pairs that are non-intersecting. Well, obviously, if some Si is greater than like A minus what we want to get, it's impossible, because the total size of everything else will be less than what we want to get, and for each pair we must use at least one vertex from like not the largest subtree, or generally like not from any fixed subtree, because we need to use two vertices from the two different subtrees. It's actually like a very well known like problem or subtask that occurs in many problems, including this one. Apparently, is that like if you have some sets of things, I don't know, balls colored in different colors, and you need to make pairs of two balls of different colors. Like the maximum number of pairs you can make is minimum of like the sum of all groups halved rounded down, and the sum of all groups minus the maximum group. So that's the maximum we can get. And it is actually achieved like greedily. You just on every in every operation you want to choose two largest sets and take one element from each and pair them. Like it will decrease the sum by 2, but also like decrease the maximum if it was unique or if it was like two largest. Otherwise, it just works like you can match almost everything. This will be the minimum. So, how is it related to our problem? Well, if the minimum is this, we're just good, right? Otherwise, like there can be only one large set, because like if there are two large sets, their sum is already bigger than the sum of everything. So if the minimum is not this, then there is one very large subtree and all the others are small. But then we can exhaust all the smaller subtrees by matching it with like what's here. And moreover, it does not matter for us like how many vertices, not how many, which vertices here are left. So we can say, okay, like let's say this is very large and everything else is small. Then we will say, okay, so those we can match to like some different vertices here. But for now, let's just try to solve recursively like in this subtree. We will have something left and we also have some matched pairs. But then I can unmatch some of the pairs if I need to, so that like I want to use all of those on matching someone here. That's always like, well, yeah. I can always use all of them. So that's pretty much it. So my algorithm will look like I will calculate sizes for all subtrees, and then I will run this procedure like it starts in the root, looks at the subtrees. If there is no large subtree, then I can just match everything except maybe one vertex. Otherwise, I will take the large subtree, I will go into it, solve the problem recursively. I have some unmatched vertices and some pairs, and now I like come back and want to match as many as possible. Like I need to use all of those, so I might have, if I have like nothing left unmatched in the big subtree, I will break some pairs to match them with those smaller sons. Do I need to actually print the matching or just the number? Just the number. Oh, then it's even easier. Like I don't need to do anything particularly. Like, I don't need to do the matching and unmatching. I know that it is possible, and that's enough for me. So I will just like run this procedure, and when I come back from like recursively solving the larger sum, I will just say, okay, it matched something. I know how many. I know how many unmatched vertices are there. If they're less than the sizes of everything else, then I can match everything except maybe one. Otherwise, I will. Otherwise, I have a lot of unmatched vertices, so I will just add the number of like the sum of the rest subtrees to the number of matched vertices I got. Oops. I guess it wouldn't be much harder to actually do that, but whatever. Do I need the graph? Like again, the correct way is to just implement what I said, but I'm interested if I can like do it without the recursion, basically. I guess I should be able to do it. So each vertex will have parent, each vertex will have a size of its subtree, and also I'm interested in the well, let's call it DP because it will be kind of DP. The maximum matching I can get in the subtree, and also I want for every vertex to know what is the largest sum. Right. So since I know that every parent of every vertex has a smaller number, instead of actually doing DFS, doing some recursive stuff, I can just run from larger numbers to the smaller numbers and like calculate everything that I want to calculate in that way. Certainly, I can calculate the sizes like that. That is super simple. But I need to, yeah. But I was worrying about like that I need to go to the largest sun, and that is like kind of I want to go recursively. And like it would be easier to do in GFS, but I can just calculate the answer for all the subtrees actually. I will just need it just from the largest, and I can like maintain those maximums while I doing it without like for every vertex running through all the suns. Yeah, I certainly could have done like without DFS if I start the list of all the suns for all the vertices, because then you just like run from larger vertices to the smaller by number, and like it is going up the tree. When you process vertex, you already processed everything below that vertex. But I don't even have to have this like vector of vectors or array of vectors or whatever for storing the suns, because I can just like when I solve for the vertex v, I will update its parent with everything I need to know, and I only need to know like of one values for every vertex. I'm just being insane here. Like obviously GFS would be good enough, and like it has the same complexity. And storing the list of children also like it's better than GFS for me. It still has the same complexity, and it's totally okay to do. But like for me, this is kind of more elegant. I don't know. Like I'm not storing unlimited information for any vertex. For every vertex, I'm just storing constant number of values, and like even storing all the sums for all vertices, like it is linear in total, the size of input. But linear in total is like in my head, it's somewhat worse than constant for every vertex. That doesn't mean like it shouldn't mean anything to you, but I'm a bit happier that I can do it like in a more elegant way from my point of view when storing less. Like it's the same thing as like when I want to solve easy problems without storing the array. Like I can just read it once and like do everything on the first read without needing to store it. Here it doesn't work like that. I need to store the tree. I cannot just look through it once. No, I don't think it should be possible. But I can do it like this, and for some reason it matters to me. actually size will be like with that vertex included, so the number of vertices below it is size -1, and that I need to divide by 2, rounded down. That's the maximum value I can achieve. Maybe it is actually small. So for like normally I need to look at the largest sun, but I have leaves in my tree, so some vertices do not have suns. So if it is not -1 and size of that is greater than this thing, then it's somewhat bad, and like I need to update my DP with so in that vertex I'm taking the maximum matching, like in the largest sun I'm taking maximum matching, and also I'm adding the size of everything apart from that largest sun. Actually, I can just do it always if u is not -1. Like, since I'm taking minimum, if size of u is small, it will just mean that like this is bigger than size of u over 2. And like this is not exactly like I took the best answer, and then I said that I can also get all the rest vertices that are in the other suns. That is not exactly correct. Maybe like dp u may be close to size of u, or like size of u over 2, I mean, and like I don't have enough unmatched vertices here, so I need to break some pairs I constructed to match everything like that is left in the other subtrees. But then the answer will be just like I matched everything except maybe one vertex, so this, and since I'm taking minimum, like it will just be bigger than I already have, which will not change the answer. And if v is not 0, I need to update my parent. I need to say that its size is increased by my size, and probably update the largest sun of pair of v, maximum is the old value, and make pair size v. Okay, I guess we haven't read problem E yet, and it is corrected, so I just need to update it, and then we'll be fine. Okay, G is also accepted, and we're left with problem E, subset product problem. I like that name. Although it might be some generating function, hardcore stuff. I'm a node-coder. Okay, let's see the problem. You are given a length and sequence of non-negative integers a for k from 1 to n. Solve the following problem. Find the product of ai for all integers I between 1 and k inclusive such that the bitwise or operation of ai and ak equals ak. Alright. I between 1 and k. So the problem for given k is like there is a last number that is like very special. And so bitwise OR of ai and ak equals ak means that ai is a submask of ak. I guess like that subset thingy. And I want to take a product of all such things. Is n times square root of this is okay? 6 seconds? It should be fine. What is the problem then? Okay, I think that just works. Okay, so the so we have like those masks of length 20. We can split them into halves, size 10 and 10. And for a given like for query kind of like I have the number ak, I need to basically I can like for every number I can maintain the product of all numbers that were I guess equal to that number on the prefix. So it's just like x to the power of how many times I had that number. And for the query, I will just run through all submasks and take product of those numbers. That is obviously slow, but we can notice that like we are adding the number to data structure in constant time, just multiplying 1 point, but collecting is 2 to the power of 20. We can try to like make those closer so that maximum of them is smaller. So I will try to split the masks into 2 halves and say that basically the left part of mask I will handle when inserting the number and the right part when doing the query. So what I want to do. So I have like mask A, and for mask A when I do the query, I want to take product over all B that are subsets. So it's like this, right? So if I split it into 2 halves, then B1 must be a subset of A1 and B2 must be a subset of A2. Right, so when I do the query, I want this to be fixed, and over these things I will iterate, or kind of like A1 and A2 are fixed. So for a query, I will iterate over submasks in the right part. But then I need to know like what is the number of masks be, or like product over all the masks be, that in the right part they're exactly this, but in the left part the submask of this. Well, okay, let's just store that. So for mask that is like on the left part it is A1 and on the right part it is B2. I want to store all product over all numbers that the right part is exactly B2, the left part is a submask. It's B1. So when I add number B to my data structure, I will run over all like super masks A1 of the left part of my mask and multiply the start numbers there. Now, like for every number, I store the product that I want to, and for the query, I will like run over all submasks here and just take the product. That's it. It like each number will be processed in time proportional to the 10th power, and that should be fast enough. That is a very weird problem for a coder. Products of empty sets are 1. Y should be a super mask of the first 10 bits of X. So okay, so here I need to replace the larger half of like larger than bits of X with Y. Okay, let's just well, it looks similar. um, I feel like this is the easiest problem of the contest. Like if you know the skirt mask trick, this is just like direct usage of that. Like there is barely a problem there. It's just, do you know this one thing? Very weird. Yeah, I do know that one thing. Exactly 2 seconds. And the time limit was like 6. So, not even close. Okay, that was much easier than the 2@Coder beginner contests I did recently. Yeah, 25 minutes is reasonable time, I guess. Alrighty. Thanks for watching. Bye.